Hello everybody, this is my group concepts presentation talking about hemoglobin binding to oxygen. And so for mine, I decided just to kind of start off with what hemoglobin is, and this is kind of just I directly took it from the page on our discussion this week, just saying hemoglobin's, a protein that binds with oxygen in our lungs and then gets travels to our capillaries, and the oxygen gets released from the hemoglobin, and our body works to kind of control, when the oxygen is going to get released from the hemoglobin by having a different pH in the lungs and having a different pH in the capillaries. So, first off, kind of talking about hemoglobin binding to the oxygen, and I kind of mixed in stuff with the different structural changes between this and the next slide, so they're kind of mixed in together. So the hemi group in the hemoglobin is non-planar before the oxygen becomes bound to it. And that iron atom is actually out of the plane of the porphyrin ring, kind of up towards the histidine, and this tends to give that hemoglobin kind of a dome-shaped appearance. And then when the oxygen actually binds to it, the hemi tends to become more of a planar configuration, so that iron comes down and tends to lie in the plane of that porphyrin ring. And I added some nice little cartoons I found on the internet. And then on this page, I kind of liked this picture because I can actually see what we were talking about in the previous slide about the hemi having a domed shape appearance, kind of how it's non-planar before the oxygen binds to it, and then here it becomes a little bit more planar. And so some of the structural changes that come with oxygen binding to the hemoglobin, the quaternary structure changes after the oxygen binds to the hemoglobin. Its 3D structure includes a pair of identical alpha and beta dimers that associate and form tetramers. And then the oxygenation of the hemoglobin alters the TR state. So before it gets oxygenated, the hemi groups are pretty well separated, which would more correspond to the T state. And then during oxygenation, that iron kind of moves and brings the iron-associated histamine down towards that porphyrin ring, and this would correspond with the R state. So the hemoglobin being oxidized alters that T and R state. And then the oxygen will then get transported from the lungs, where the partial pressure is relatively higher to the tissues, or where the partial pressure is relatively higher and gets transferred to the tissues where the partial pressure is lower. So therefore in the lungs, all of the hemoglobin is nearly saturated with oxygen, but then when it moves to the tissues, the oxygen saturation kind of tends to drop off. So here we're kind of talking about the binding capacity. So when the PO2 is high, as it tends to be in the lungs, that oxygen is going to want to bind to that hemi group. And then when the PO2 is lower, such as when it's in the capillaries, the oxygen is going to want to release from that hemi group. On the left, I added in that picture, it's kind of a lot going on, and there are a lot of numbers. But if you look for the PO2 numbers, you'll see that the numbers on there correspond to high PO2 in the lungs, and then lower PO2 in the capillaries. And then the partial pressure of gases, temperature, and the pH are going to affect that binding capacity of the hemi group. So in the lungs where you have that high PO2, you're going to have a low temperature and then a lower pH as well, which is going to help that oxygen want to bind to the Hemi group, whereas in the capillaries, your PO2 goes down, which is going to give you a higher temperature, and your pH is going to go up, which is going to cause the oxygen to want to release from the Hemi group. And lastly, talking about CO2 kind of interacting with water and what that does. And so CO2 can react with water, and this forms carbonic acid. And the formation of carbonic acid is going to cause a decrease in the blood pH in our bodies. And then, so in our bodies we have a lot of different buffer systems, but the one in this case we have a bicarbonate buffer system, which would work to remove ions to prevent the pH from becoming too acidic, in this case with that carbonic acid. So a hydrogen on that carbonic acid would actually dissociate to join the hydroxyl group on the base to form water and sodium bicarbonate, which this would still cause a decrease in the pH, causing that oxygen to release from the Hemi group. And this is actually a term that we learned, which is called the Bohr effect. So as your blood plasma pH decreases, becomes more acidic, your hydrogen ions increasingly bind to the hemoglobin amino acids, which will lessen the hemoglobin's affinity for the oxygen. And then I thought that was just a cute little cartoon having to do with hemoglobin and oxygen. All right, thank you.